Hello and welcome to Building Resilient Log Aggregation Pipeline with Elasticsearch and Kafka. My name is Rafał and I work for Sematext, a company that you probably heard about. I talked about it for a minute when starting the conference. So we build products for DevOps, basically SPM and Logzine. SPM is all about monitoring, Logzine is all about log centralization, and we provide professional services around those and log aggregation and custom tools that you build. But let's get on with that. So what I'll be talking about in the next 30 minutes is a log centralization, building a pipeline that's resilient, that allows you not to lose any data, and basically works even if you have spikes in the data. We'll talk a bit about storage and analysis first, which in our case will be Elasticsearch. Of course, on top of Elasticsearch, you can use different tools to visualize the data, but we'll skip that today. So there is Kibana, Grafana, and all the other tools out there. We'll talk a bit about centralized buffering and buffers in general. So for centralized buffering, we'll use Kafka today. Of course, there are other tools as well, like Redis. But today, the focus will be on Kafka. Finally, the last part of the presentation will be about log shipping and some considerations when it comes to log shipping. What type of buffer to use, what protocols, and if you should parse or not, how to log and do it like that. So let's start with the general architecture of the most common log aggregation pipelines that we have the opportunity to work with, either in our environment when eating our own dog food or whatever, working with clients and designing architecture for them. So basically, you have a bunch of servers, applications, machines, or anything like that that do produce some kind of logs. That can be log files written on the disk. They can be sent directly to syslog. They can be directly pushed to some other system or anything like that. So that's the left part of the general architecture. Then we have some kind of centralized buffering for resiliency, for to being able actually to make it work when we have too much data to process by our analysis engine, which in our case will be Elasticsearch cluster. So first of all, we'll focus on Elasticsearch, and I'll tell you mostly about how to properly configure it, what you can expect from different kind of nodes, what are the requirements for different kind of nodes, and things like that. I'll keep the focus on Elasticsearch mostly because this is the most common part that fails. It's not that Elasticsearch is bad, it is just sometimes hard to configure and sometimes hard to keep up for Elasticsearch with the data flow in general. So let's start with that. When you take Elasticsearch out of the package, it works as a client, data, and a master node. However, it's not good to have Elasticsearch work like that. You've probably seen that picture or similar picture like that already if you work with Elasticsearch. So basically, there are 4 types currently of Elasticsearch nodes that can run inside the cluster. We are talking about Elasticsearch 5.0 currently, which was released recently. So first of all, the client nodes, the ones that are handling your queries and the data. You push the data and your queries through the client nodes. They aggregate the data from other nodes, like the data nodes. They do not hold any data, so the only thing is aggregating the data and returning the results. Then we have the data nodes, the workhorses of your clusters that have parts of your data that write the data to the disk that needs to process the queries, partial queries on that data. In addition to that, the new type of node in Elasticsearch 5.0 are the ingest nodes, basically a log stash inside your Elasticsearch cluster. You can do grokking, you can do processing of those messages that you have already in Elasticsearch. So if you would like, for example, to avoid log stash and do processing on Elasticsearch, that's also possible currently with the ingest nodes. Finally, the master nodes, the brains for your cluster. Very important role, though usually forgotten about, the ones that do process the cluster state. And when it comes to the master nodes, you should remember that they are mandatory. You should never run a cluster in production without master nodes being present. You should have at least set the discoveries and minimum master nodes to 50% plus 1 of your master eligible nodes. Otherwise, you're vulnerable to network partitioning, and that will probably, in 99%, cause your data to be corrupted. And that's nothing we can do after the network partition happens. And for example, you end up with multiple clusters instead of a single one. So the first thing that comes into mind when we handle Elasticsearch is create one big index and just put everything into there. But that's a big no-go when it comes to time series data. Why? Because it's not scalable enough to handle a lot of data in a single index. The indexing will slow down with time, giving you to a certain point that you will not be able to keep up with your data flow, and you'll just start falling back. In addition to that, you run into expensive merges, which is all why the indexing is slowing down eventually after time. Finally, delete by query. When you want to remove some of the data, you will need to delete by query, which first of all is not supported by default by Elasticsearch. You need a plugin, but second of all, it causes even more merges, which causes another CPU and memory and I/O exhaustion, and again makes the indexing slower, causing fallback and not being able to search and index the data in near real time. So what we can do. First of all, daily indices. This is a basic thing that we usually start with. A single index per day or single index per week or anything like that. Indexing is faster because the indices are smaller, so merges are less expensive. Deletes are cheap because we just delete the whole indices from the file system. We do not delete parts of the data from Elasticsearch itself. Search can be performed only on the data that is needed. So for example, if we just need to search for 2 days worth of data in our logs, we just specify 2 indices like 22nd and 23rd, and we're good. Finally, static indices, the ones that we do not index to, are very good candidates for caching by the operating system. So again, we gain performance. The thing is that, for example, in the coming Black Friday, we start to get problems with that approach. The most common problem is that the indices are not balanced well. During Black Friday, when you have a lot of customers, for example, in e-commerce, you log a lot more. And the thing is that Elasticsearch is not very good when balancing the indices that are not similar in size. So you will end up with some of the nodes having more data, some of the nodes having less data. That can become a hotspot, and you may encounter cluster instability, which is not very easy or pleasant to work with. So what we can do, we can switch to so-called size-based indices, which are optimal for time-based data. In size-based indices, the idea is to have some kind of limit, a hard limit on the amount of data you can put in a single index. For example, in our tests that we did on for various conferences, and when dealing with our own environment in Amazon virtual machines, we see that the amount of data that is good for indexing is from 5 to 10 gigabytes per shard in an index, depending on the machines that we use. If you have better machines, you're more likely to be able to index 10 gigabytes of data without the drastic drop of indexing. So the idea is to just index data, check periodically, or use the rollover index API in Elasticsearch 5.0. When the size limit comes too close or is above, or the index size is above the size limit, we just switch the alias to the new index, and we just index the data, and we keep on adding indices like this. The nice thing about that approach is that we merge together small indices. Imagine that you have lots and lots of data, lots of types of applications that you gather the data from. For example, Nginx logs, Nginx logs, Apache logs, some applications that are only run periodically, like once every day, and things like that. So if you keep a single index for that application, you will end up with hundreds of smaller indices around the cluster. And again, that's not something that Elasticsearch likes to work with. You will end up with problems around the master nodes, you will end up problems with memory, or even statistics if your I/O is not good enough. So when it comes to size-based indices, to summarize that, it's better for indices balancing, you will end up with fewer shards, it's easier to handle for Elasticsearch. And of course, that gives us better cost in terms of how the hardware is utilized. However, that's not all. Keeping the indices on a size-based manner, it's one of the things that we need to care. The other thing is, for example, Elasticsearch configuration. Keep in mind that, for example, index refresh, which is all about how your data is visible, how fast it is visible after it is sent to indexing, also matters when it comes to throughput of your indexing. For example, with the test with 1 second, the default refresh rate, we got a baseline throughput of 100%, let's call it. It was about 2,000 logs per second on a very small laptop. Then increasing that to 5 seconds gave us 25% increase in throughput, or indexing throughput, and 30 seconds gave us 75% increase of the base throughput. So you can see that that matters. And in addition to that, I've mentioned that segment merging, right? The process of copying few segments and combining them together to give you one bigger segment. That's done because in Lucene world, indices are immutable, which means that once they are written, they cannot be changed. So when delete happens, or when there are too many segments, Lucene in the background, the library behind Elasticsearch, just copies them and merges them together. So, but because in log aggregation tools, we usually do visualize logs and do not search too much on them, like you do a search and you build up dashboards. We can optimize the segment merging and allow ourselves for a bit more segments because aggregations do not care about how many segments you have. They work on, for example, dog values. So we can actually lower down the pressure of the merges by configuring 3 properties. They are all prefixed with index merge policy at the bottom. So if you go with the higher than the default segments per tier, you'll get a bit more segments, which gives us a better throughput of indexing. The same with max merge advanced. This basically configures the merge policy, so-called, but let's not get into too much details. And finally, the max merge segment, which is by default the 5 gigabytes. If we lower that down, for example, to 1 gigabyte, which we, again, on AWS, we think that 1 gigabyte is more or less good for log aggregation pipelines, we get a pretty decent performance of and throughput of indexing because Elasticsearch focuses on smaller segments, which means less I/O operations in the background. So, in addition to that, index only needed fields. So if you do not search on some data, do not index it. It's just a waste of resources of your servers. Use doc values to lower the pressure on the garbage collector. For aggregations, do not index the source field. Because you already have the data in index fields, it doesn't make sense. Finally, do not store the all field because it's usually the field that you gather from all the other fields, so you already have that information. But that's not all. You can also optimize the data layer of your Elasticsearch cluster, which means the data nodes in your environment. So the most common thing that you go for is going for hot and cold nodes, so-called hot-cold architecture, or even hot, warm, cold, depending on the needs. But the general idea is to divide your data nodes into at least 2 layers. First of all, the hot node is the one that will handle the most operations when it comes to indexing, so all indexing and new real-time searching. For example, if you need to search mostly on a 1 day worth of data, then you will put a single index on a hot node. Then on the cold nodes, those are more like an archive. They will run long-running searches. They will do all the extensive operation on the archive data. For example, 90 days worth of data. You can run them by specifying a node attribute tag in Elasticsearch 5.0 or node for tag in Elasticsearch in the previous Elasticsearch version, or just include that property in your configuration depending on what you would like to do better for your organization. So the idea here is to, when we create an index, for example, for the 22nd, we say index routing allocation exclude tag, the same tag as we specified in the startup parameter, and say cold, which means exclude cold nodes from creating the index, and the bottom line is include hot nodes. So the index will be created only on the hot node. Then we index the data. So we index. When the day comes to an end, I'm showing that on a daily indices, but the same thing is about size-based, but it's easier to explain on the daily indices. So we create a new index, and we start indexing to that new index. For example, we have a log stash configured to index that, any log shipper. Then, when the indexing to the old index stops, we just say the similar command, but we update the index settings, and we say exclude hot and include cold. What Elasticsearch will do, it will just copy the index to the cold nodes without any kind of downtime, only some resource utilizations, which again can be configured depending on the needs. So it will go like this. It will copy the index, then we'll create another index. Again, we copy the old after the day ends. So after a few days, we will have a single hot index on hot and more indices on cold. The thing to remember here is resources for each of the parts. So the hot tier in Elasticsearch requires good CPU and lots of I/O because you will index lots and lots of data, and you will need to search on that data if you want to do reports, for example, on the recent data that is on hot. When it comes to cold tier, you are memory bound. Lucene needs a static amount of memory for all the indices that are opened and ready to be searched. So the more data you have, the more memory you will need. And again, some decent amount of I/O will be needed because Elasticsearch communicates internally between the nodes and sends so-called stats about the indices. So this is when the I/O is needed. Also for backups or any kind of archive searching, I/O is a good thing to have. For hot tiers, SSDs, as usual, are your friends. If you can't afford SSDs, write 0 with spinning disks. But again, the more IOPS you have, the better. What we gain from that? We optimize costs, that's for sure, because we can choose different hardware. We have better performance because we can actually optimize one or multiple hot nodes for indexing and searching, and we isolate the long-running searches not to interfere with the indexing operations, which is, again, something good because we don't know our management to actually say, hey, something is not working, the queries are running for more than 5 seconds. So, again, nice thing. A few more things about the needs of each of the nodes. The client's nodes are, of course, the ones that will be utilized, but they do not contain any data, so we do not need fast disks there. We need a bit of CPU. The more CPU, the higher the throughput of the queries is, and we will need memory, because again, the more documents you send through the client nodes and the more queries you send, the more resources will be utilized. When it comes to the data nodes, we already mentioned some of the things. When it comes to the ingest nodes, remember those are the log stash instances around your Elasticsearch cluster, inside your Elasticsearch cluster. So again, no data there. High CPU and memory usage depending on the amount of rules you have in your configuration. If your pipeline is defined to have multiple grok rules, those are regular expressions. They will consume CPU, and the more documents you process, the more memory you will need to process those documents. So that's again, something obvious. The master nodes, and this is, again, something I would like to mention for you to remember. They will use lots of CPU and lots of memory. The more indices you have in your cluster, and the higher, the more complicated mappings you have inside Elasticsearch. So if you have hundreds of fields and hundreds of indices, you can expect your master nodes to use a lot of memory. So that's, again, something to consider. Size-based indices help with that. So again, and of course, lower the data retention if you can't afford enough memory for the master nodes. So let's now put a focus on the centralized buffer. In our case, we said that it will be Kafka, right? So we have Elasticsearch put on site. Let's now talk about Kafka. Why Kafka? Because first of all, it is fast, very fast, and very easy to use. If you take out of the box Kafka, it will work very well without any kind of configuration adjustments. Of course, if you want to tune it, you can, but out-of-the-box experience is very, very good. It is very easy to scale, it's fault-tolerant, highly available, battle-tested. Multiple organizations use it for handling their logs, and they are processing millions of events per second with even small Kafka clusters. It supports streaming, so if we want to do any calculations on top of streams, again, with Kafka 10, 0.10, it's possible. Finally, it works in publish-subscribe mode, so it's very easy to send our logs to multiple destinations. So what is the basic architecture of Kafka? Very simple. We have the Kafka nodes around a Zookeeper ensemble, and the Zookeeper ensemble is at least 3 Zookeeper nodes that will be used by Kafka to perform, for example, leader elections, atomic operations, and things like that. Basically, a helper for the Kafka cluster to be stable and to do all this algorithm around leader election. Why reinvent the wheel and there is already a tool that can do that? So Zookeeper and Kafka. So this is a thing you need to care about when running Kafka. So how does Kafka store data? It stores them in the topics. For example, you can have one large topic for all your data, but you can have multiple of those if you want to have some kind of prioritization of your logs. If you want to have your security and access log to be prioritized by your consumers, then you can create multiple topics for depending on your source and write them on disk. Topics can be split into partitions. And of course, partition can have a leader and replicas. Again, for fault tolerance and highly available Kafka cluster, we need to have at least a few partitions with replicas to be able. Keep in mind that if you want to scale Kafka, you need more partitions, and I'll tell about that in a second. So again, when we scale, we first imagine that we have a single Kafka node, we create a topic with called logs with a single partition, and we can have a single thread reading the data from there. If you add multiple threads, that won't do any good, because you have a single consumer that can read from a single partition and not to get duplicates. If you connect a second consumer, Kafka stores offset per consumer, so it will just get the same data twice. So if we want to scale that and parallelize computing, we just create multiple partitions. If we want to have fault tolerance and highly available cluster, we spread that to multiple nodes and multiple partitions. And that way, we can create more consumers and have a more parallelized load on both consumer sides, which consume messages from Kafka, and both of Kafka, because Kafka, in that case, will use hardware from multiple nodes. Things to remember when using that. It scales by adding partitions, not threads. Offsets are stored per consumer, so if you want to have multiple sources, destinations of the data, like archive data in S3, index to Elasticsearch, sent to some kind of other processing pipeline, this is very easy. You just create multiple consumer groups. Replicas are used for high availability and fault tolerance, and keep the number of consumers equals to the number of partitions, because otherwise it doesn't make sense and it doesn't scale. And one thing I forgot, the more IOPS, the better. If you want your Kafka to be processing more messages, just add more IOPS or spread to multiple hosts in that case. Finally, the shippers. What about the shippers? So whenever choosing a log shipper for you, you should ask yourself 3 major questions. First, which protocol should be used? Should I use UDP, TCP, and what about acknowledgements or TCP? Second of all, what about the buffering? Should we use a centralized buffer, or maybe we should use the local buffer with the centralized buffer? I'll talk about that in a second. And the third question is, should I log in JSON, or should I pass the data? In general, if you can control how your applications are logging, log in JSON. Because that means that if you push the data to Elasticsearch, it doesn't need to be parsed along the way, which means that you will save resources. CPU utilization will go down. If you can't control that, just use Grok or any other tool that can structure your data to JSON so that Elasticsearch will understand that. So whenever we talk about buffers, we talk about performance and availability. If we talk about log shipper performance, there is usually a mention of batches and threads. So how large the batch of a single batch is, so how many messages are sent per request through the network, and how many threads the log shipper will use to do that kind of operations. When it comes to availability, we talk usually about what to do when the central buffering is gone. Like here, what to do when Kafka fails. It doesn't happen, but okay, it happens. But in general, what to do when such unlikely event happens. So there are multiple buffer types, of course, when it comes to log shippers. For example, you can consider a local file that you write to, for example, from your Java applications as a local buffer, right? Because it buffers some data. So the simplest approach, the easiest to scale, and having the least moving parts is to have the approach like on the left. So you have an application, some kind of buffer like files that sends directly to Elasticsearch. However, that has its drawbacks. If that server is gone, you lose the data. So no reliability when it comes to that kind of buffering. Of course, for example, log shippers like our syslog have multiple type of buffers like disks, memory buffer, or combined approach like memory-assisted queues in our syslog that can store data in memory, and then after, if the memory is full, it will write to disk so you don't lose the data. And the second thing is think about the wider approach. So should I store and buffer the data on source, or should I use the centralized buffer? So the approach we are currently discussing, the one on the right. So application uses some kind of shipper to ship to a central buffer, and then we read from the central buffer to store in our analysis engine, which is Elasticsearch in our case. And the thing is that the approach on the right approach, allows us also to add extra features like time to live on top of Kafka and things like that. So again, simple, reliable, depending on your use case, depending on the needs. With them, if you like to have not to lose logs, use the approach on the right. When it comes to protocols, we again have the considerations about UDP, which is very good for application, but again, not reliable because it can lose data. TCP is not reliable as well. Why? Because it only acknowledges on the network layer. So if your source sends the data to the destination and the destination do not have any application level acknowledgements, your data can again be lost because the data can be, for example, shipped to a socket. Socket can acknowledge the data, but still the application that accepts the data didn't do anything with it. The node dies and you lose data. So you should use one of application levels acknowledgement protocols like HTTP, which is used by Logstash, our syslog, FluentD, or RELP, Bits, Kafka, anything like that, that allows you to do and actually automatically does application level acknowledgements. Finally, when choosing the log shipper, once again, consider if you would like to have a simple approach, like going through the socket from the application, sending and using our syslog or anything like that to send to using HTTP to Elasticsearch, or maybe you want a more complicated but more sophisticated, but a better solution, more reliable, more fault tolerant, that uses a centralized buffer with a consumer that reads the data. So finally, what I would like to mention today is keep in mind that there is also one piece left of all that what we discussed now. This is the operating system on top of your hardware that you should care about. Say no to swap, then no matter what you do. Swapping is bad, especially for the JVM apps. JVM hates swapping and will just make your software poor and behaving very unwell. Set the right disk scheduler depending on the disk you use. For example, if you use SSD, use the deadline scheduler. Use a proper mount options if you are using ext4. So data write back, no barrier, and no directory time and file times. And finally, for bare metal, take a look at your CPU governor, the one that takes care of your power management. and disable transparent huge pages. For example, MongoDB developers tell that you should disable that. In most Linux operating systems, transparent huge pages are enabled by default, but are virtually disabled because the number of transparent huge pages is set to 0. I have 5 seconds, so let me just repeat that. We are hiring. If you would like to work with that technologies, if you would like to be a DevOps or are a DevOps that looking for a change, come join us, talk to at our booth. Thank you for listening to me today. Hopefully you get something out of the presentations. If you want to talk to me or any guys at Sematex, we have a booth right there. And once again, thank you and enjoy the rest of the conference.